Exercise is one of the most accessible and powerful lifestyle interventions for enhancing cellular health, with its ability to induce autophagy being a central mechanism by which it confers broad protective effects. Both aerobic and resistance training impose a controlled form of metabolic stress on the body, temporarily depleting cellular energy reserves, increasing oxidative demand, and triggering adaptive responses that ultimately strengthen the system. One of the most beneficial of these responses is the activation of autophagy, a cellular self-cleaning process that eliminates damaged organelles, recycles misfolded proteins, and restores internal order at the microscopic level. The autophagic response to exercise is primarily mediated by two key energy sensors within the cell: AMP-activated protein kinase, AMPK, and sirtuin-1, SIRT1. AMPK becomes activated when cellular energy stores, specifically ADP, drop during physical exertion. This activation signals the need for increased energy production and conservation, initiating a cascade that includes the suppression of mTOR, a well-known inhibitor of autophagy. As mTOR activity declines and AMPK rises, cells begin shifting from growth mode to repair and recycling mode. SIRT1, a longevity-associated deacetylase that responds to changes in cellular NAD levels, is also upregulated during exercise, particularly under endurance conditions. Once activated, SIRT1 works in parallel with AMPK to initiate autophagy, enhance mitochondrial biogenesis, and protect against oxidative stress. The type and intensity of exercise determine the degree to which autophagy is activated. Aerobic training, such as running, swimming, or cycling, has been shown to stimulate systemic autophagy across multiple organs, including the brain, liver, and skeletal muscle. This broad activation is thought to underlie many of the anti-aging and neuroprotective effects of regular cardiovascular exercise. On the other hand, resistance training, like weightlifting or bodyweight workouts, induces localized autophagy in muscle tissue, helping to remove damaged proteins and stimulate muscle repair and growth. Importantly, even moderate-intensity exercise performed consistently appears to produce cumulative benefits for autophagic efficiency, particularly in older individuals or those with metabolic syndrome. Exercise-induced autophagy is also linked to improved insulin sensitivity, reduced inflammation, and enhanced immune function. By periodically stressing cells through physical movement, the body becomes better at managing energy, cleaning up intracellular waste, and adapting to future challenges. In the brain, exercise-induced autophagy has been associated with improved synaptic plasticity and cognitive function, while in the cardiovascular system, it helps maintain endothelial health and prevent atherosclerosis. These effects collectively point to exercise not just as a means of fitness, but as a deeply regenerative and preventive intervention at the cellular level. From a nutritional standpoint, supporting the autophagic process around exercise involves careful timing and balance of nutrients. Before exercise, consuming a small amount of complex carbohydrates, such as oats, fruit, or sweet potatoes, can provide a steady energy source that enhances workout performance without significantly inhibiting autophagy. These pre-exercise carbs are especially beneficial for prolonged aerobic activity, where glycogen depletion is more pronounced. However, fasting workouts or low glycogen sessions may further amplify AMPK activation and deepen the autophagic response, depending on one's goals and metabolic flexibility. After exercise, the priority shifts to recovery and rebuilding. Consuming a source of lean protein, such as eggs, fish, tofu, or a quality protein shake, within an hour or two post-workout supports muscle repair and synthesis. This replenishment phase complements autophagy by ensuring that the body has the raw materials it needs to replace what was cleared out. Additionally, pairing protein with antioxidant-rich plant foods such as berries, leafy greens, or turmeric-spiced dishes can help manage oxidative stress without fully blunting the beneficial inflammatory signals that drive adaptation. Long-term, consistent exercise promotes an efficient and well-regulated autophagy system, helping the body stay metabolically flexible, resilient, and resistant to age-related diseases. Unlike pharmaceuticals or extreme interventions, movement is an inherently natural trigger of cellular renewal. It works with the body's biology rather than against it, and its effects are both immediate and cumulative over time. Whether it's a brisk daily walk, regular gym sessions, or participation in sports, physical activity sends a clear message to the body: adapt, repair, renew. In conclusion, exercise activates autophagy through the dual stimulation of AMPK and SIRT1, creating a cellular environment that favors repair, resilience, and metabolic health. This natural process not only clears damaged components, but also lays the groundwork for improved function across tissues. With supportive nutrition, pre-exercise carbohydrates to fuel performance, and post-exercise protein to support regeneration, physical activity becomes one of the most holistic and sustainable strategies for promoting cellular rejuvenation and long-term vitality.